Good afternoon and welcome to this webinar hosted by Ramboll and Force Technology on the challenges and opportunities in repurposing existing hydrogen infrastructure. A little bit of practicalities. First, during the webinar, you will not be able to speak. We have muted all of you because there are many signed up for this event, but you can ask questions and comments in the chat, and please also write your name. We will be video recording the webinar, and that will be shared after the webinar together with the slides. We will be answering some of the questions during the webinar or in the end. And if there are still some questions and discussions to be made, then we will invite you to enter the LinkedIn group as you can see on the photo here, the Hydrogen Handling and Transportation group, where you can continue some discussions. The agenda for today. First, there will be a short introduction to the topic. Then Ditte will tell about materials in hydrogen infrastructure, and Geir from Ramboll will tell about pipeline design and repurposing. Yeah, Ditte?
Thank you, Trine. Well, to start with, what is all this fuss about? Is hydrogen even a thing? Well, in Denmark it is, yes. We already have industrial clusters producing hydrogen. There's focus on pipelines. And in order for green hydrogen to be produced, we need the renewable energy. And as you can see from this map of Denmark, there's plenty of offshore wind. By 2030, we expect to have 4 gigawatts of wind power and even 35 gigawatts by 2050, and 10 times the solar power of today. Also resulting in 14 gigawatts of electrolysis capacity. And as you can see from this map, the yellow lines going down to Germany for hydrogen export is high capacity hydrogen infrastructure to be planned. And the dashed yellow lines are potential high capacity connections from energy islands offshore, producing hydrogen from offshore wind. So yes, indeed, it is a thing. Looking at a European scale, we have the vision of the European hydrogen backbone. It's an infrastructure vision covering 28 countries by 2040, and is a gradual creation of a dedicated hydrogen infrastructure. And it's going to increase the resilience of the European energy system. We all know the geopolitical situation right now. And looking at the map, all the yellow lines are new dedicated hydrogen infrastructure. But approximately 60% of the network, the dark green ones, are repurposed infrastructure. So, well, blending or not, repurposing is a really important step because at present, we do not have the hydrogen production to fill this infrastructure. There are different views on the blending and the blending levels. We have the UK project, H21, stating that current appliances are designed to work with hydrogen blends up to 23%. We have the US National Renewable Energy Labs being a bit more hesitant and not clear on what percentage of hydrogen is acceptable in existing appliances. And then we have the IEA with the plot to the right, where you have Germany to the far left with 2% blend limit, the light blue one, and up to 10% blend limit under certain conditions. So this is highly relevant to dive into the perspective of repurposing existing infrastructure, because it is going to happen. But hydrogen, does it even enter the material? Blending or not, it all comes down to sufficient amounts of hydrogen present in a susceptible microstructure and mechanical stresses. And in the end, this may cause hydrogen embrittlement. This is something we can use actively when assessing materials for hydrogen. We cannot put a specific limit on each of these circles, but in the center, this is where hydrogen embrittlement occurs. So if we have a very low mechanical stress level, the green circle, we can allow more hydrogen and a more susceptible material, the red and the green circles, and still avoid hydrogen embrittlement. If we have a very susceptible material, we need to, and we're not able to handle the hydrogen environment because it is 100%, then mechanical loading is a handle to turn on. And if the conditions of hydrogen embrittlement are met, we can see how it manifests itself in the material. As you can see from this tensile test sample, you would typically in a steel have a ductile behavior with some necking, but if charged in hydrogen, you may experience this brittle behavior as we see to the right. In a scanning electron microscope, the fracture morphology would be this intercrystalline one, typically. And this is what we would see at pipeline steels X42 to X80. And the damage may occur sometime after hydrogen exposure or after years of operation. Well, how and why does hydrogen enter the material? It may be due to process or service conditions, diffuse under the influence of any gradient. That could be temperature, pressure, pressure fluctuation, strain, and a concentration gradient. And as an example, if we have a pipeline wall with 100% hydrogen on one side and nothing on the outside, we may have a stabilization of this pressure hydrogen gradient through the steel wall. Hydrogen sources may be even from manufacturing, steel making, welding, corrosion processes, cathodic protection, hydrogen transport, and electrolysis as service conditions, of course. But in order for hydrogen to enter the steel, it has to dissociate. And that means going from H2 to H plus atomic hydrogen. And we have several driving forces for this dissociation. Partial pressure of hydrogen is one of them. Surface chemistry. Then we may have effects inhibiting this dissociation at the steel surface. That could be a coating inhibiting the steel, the hydrogen uptake in the steel. It could also be an oxide layer and other available species near the surface. As we can see to the right, this green layer could illustrate an oxide or a coating, and the red is the dispersion of hydrogen going down into the steel. And illustrating this through a crack tip, we would have the highest hydrogen concentration, just visualized by this blue line, at the crack tip. So you have hydrogen collecting at the plastic zone in front of the crack tip, causing further crack propagation once it starts. And some of these driving forces for hydrogen dissociation include moisture and hydrogen sulfide. As you can see from this plot to the right, all bars in the red area increase the hydrogen uptake as compared to 100% pure hydrogen. So moisture is something to look out for. And we know from oil and gas that hydrogen sulfide accelerates the hydrogen uptake in steel significantly. On the contrary, we have oxygen and carbon monoxide inhibiting or limiting the hydrogen uptake in the steel. And that's been discussed mainly, I guess, on a European level. And it's still a debate because would it be possible to add a bit of oxygen to the hydrogen infrastructure to inhibit the hydrogen embrittlement of steels? Well, I guess the risk of a detonating gas and end user complications are buried that at present, but studies on the effect have been carried out. As we see on the plot from the right, we don't have an effect of hydrogen nor the oxygen at very low delta K levels, but the oxygen has an inhibiting effect, especially at intermediate delta K levels. The same goes for this study where oxygen is supplied in this horizontal part of the curve, and as oxygen is removed and we go to 100% hydrogen, we see a steep uptake. That's just examples. But in the context of repurposing, this is very important, but because if we have a pipeline with an oxide layer from corrosion, years of exposure, it may actually inhibit the hydrogen uptake in the pipeline. So an old pipeline could be beneficial. But oxygen or not, how do we in general evaluate material compatibility in hydrogen infrastructure? It's not only just the pipeline steels, but also the associated components. And one generally accepted approach is to consider the ISO TR 15916, which is basic considerations for the safety of hydrogen system. And it contains several tables. Well, one of them lists several materials ranged from extremely embrittled to not really embrittled at all. based on a focus on fracture mechanics and permeation testing. And we see especially the austenitic materials performing well, and even low alloy steels being quite embrittled. Diving a bit deeper, we see that a widely used material like cast iron, ductile iron is rated not suitable, whereas a range of alloys that we know are already used, austenitic stainless steels, look well, but low alloy carbide steels receive an E, which is evaluation is needed. Through testing would be the best approach. But how do we evaluate by testing in the smartest and most realistic way? This is an example of how an embrittled material can be used if you just consider the holistic design and these 3 circles we discussed. So we have an embrittled material. This is for hydrogen pressure containers, so the environment is 100% hydrogen. But through mechanical design, critical defects have been engineered into the material to make sure that you would have slow leak before break or burst. So that's just an example of how a more holistic approach could be used to still design safe components. And hydrogen storage in general is a key focus for this green transition, also ramping up before we have a dedicated hydrogen network. Because where do we put the hydrogen that is produced? We at FORCE are part of the efforts to prove fitness for purpose of a broadly used material like cast and ductile irons. And as just mentioned, they were rated not suitable, so not permitted by relevant regulations and standards, such as ASME 3112. But it has some major benefits on cost, mechanical properties, castability, and is in competition and replaces welded and bolted structure. And we know that welds increase the risk for hydrogen embrittlement due to possible welding defect and hard zones. We also know that it's recommended to minimize the amount of bolted sections in hydrogen infrastructure. So this could possibly be an option because we also need to look at lower cost materials for resilience, a broader material sourcing. We know the geopolitical situation, and just in general to lower the cost of green hydrogen. But as you can see to the right, ductile cast iron consists of a quite inhomogeneous microstructure. We have these dark spots, which is the graphite nodules. And this is a scanning electron microscope image of a brittle fracture in this material. So of course, everything needs to be well tested in order for us to ensure a safe hydrogen service. But besides investigating use of low-cost materials, also new alloys are being developed for hydrogen applications. And we often receive the questions, what are these H2-ready steels, these new steel types? Well, it's basically a focus on chemical composition. So using microalloying elements, strong nitride and carbide formers, that would be vanadium, niobium, titanium, and these have a strengthening effect, but also a hydrogen trapping effect. And that's being investigated quite heavily and researched, because if you can introduce hydrogen traps into your steel, you know where hydrogen will go and collect, instead of collecting at a crack tip, accelerating crack growth. But more importantly, the thermomechanical rolling process is widely used. Instead of cold forming a plate, you use a intermediate temperature. It's not a hot rolling, but it creates a fine-grained microstructure, which increases strength, toughness. Toughness is important for hydrogen embrittlement, and weldability. And it introduces a homogeneous microstructure, and often, of course, high cleanliness, low impurity level is desired. But in the end, the final susceptibility to hydrogen embrittlement will depend on a number of parameters. But for repurposing comparison, there's been some comparisons between modern and vintage steels. This is an example from the Highline project, where we have at the top a vintage 1980s pipeline steel and a new modern steel. We can see it's much more fine-grained. Looking at the composition, we also see a lower carbon equivalent, which is quite important for welding properties. Also fewer non-metallic inclusions. And looking at permeation testing through these steels, does hydrogen diffuse through the steel wall? We see a significantly higher diffusion rate through the steels that are modern. That may be important in an initial phase, but during long-term exposure, the vintage steels will probably reach a steady state comparable to the new steels. But this is a general focus on pipeline steels. What about the welds? That is the most critical area of the pipeline because you have inhomogeneous properties compared to the long sections. The Sandia National Laboratories have tested welds versus base metals. This is fatigue crack growth rate curves for X70 and X60 steels at 80 bars. And 80 bars is a very relevant pressure for the European hydrogen backbone infrastructure. That's a normal pressure for onshore gas infrastructure. And the black curve you see is the S&P 3112 master curve. And we see the results are below this master curve, and that there's not, it's quite a similar behavior for weld and base metals. This, of course, needs to be studied in more detail, but it's a promising sign. Further, they also tested fracture resistance in vintage and X52 to X80 steel, so different strength classes. And I've encircled the X80 steels, showing that even though they have a much higher tensile strength, the fracture resistance is similar. And the squared are the vintage X72 compared to the modern X72. And again, it's not as distinctly different fracture resistance. It points to the risk in repurposing is mainly related to the uncertainty of defect level and that we don't know much about service history when repurposing. So that is a promising result. But more testing is needed because hydrogen occurs at this critical combination of stress, material susceptibility, and hydrogen exposure, which we cannot put a limit on. So test is needed, and this is just an example of how ASME was changed based on testing. So it allowed the use of X70 steels at higher design pressures. But tests should be targeted. And for repurposing, the S&P 3112 demands a huge test scope. We believe that targeted testing would be smarter based on review of a specific pipeline section, knowing where the defects are and of what size. And this use of holistic approach and engineering critical assessment of defects, taking this into account would provide a more sound evaluation of the actual condition for repurposing. So we believe that is the way to move forward, because we do have a lot of data already on materials in hydrogen environment for pipeline steels. Again, the risk is that at the uncertainty of the defect level. Here we have the S&P 3112 master curve and X52 through to X100 pipeline steels, again showing quite similar behavior. And worth noting that at low delta K levels, we don't have the effect of hydrogen at all. This is the center image is an example of relative fracture resistance in air or nitrogen compared to 1% hydrogen up to 100%. We don't see a significant difference on 1% versus 100. And that's very relevant for the blending discussion. Similarly, here we see the ASME fracture resistance limits and X60 to X80 steels performing well at various hydrogen test pressures. So fracture mechanics testing is still very important because we haven't not gotten all the answers yet. Force Technology will have the first autoclave for fracture mechanics testing in hydrogen atmospheres in Denmark. And that is for us to contribute to this evaluation of repurposing potential of hydrogen infrastructure, because when does hydrogen cause damage? So during next year, we'll have static and dynamic testing in 100% hydrogen. We'll be able to test up to 500 bars hydrogen from -20 to 200 degrees Celsius. And this will also include the qualification testing needed by S&P 3112. And that's making us part of the Danish Test Center for Hydrogen, together with Danish Gas Technological Center and funded by Green Labs DK. And working with pressurized hydrogen, the ATEX zone requirements change from 2B to 2C. And this is not only in the field and in the design phase this needs to be considered, it's also highly relevant in our laboratories. The center image is our current autoclaves, which we thought were quite impressive, but apparently we cannot operate them with hydrogen. It requires a different section level. So this has, of course, like many other places, required a transition of our laboratories. One thing is these standardized small-scale specimens that can tell us a lot and sort out many parameters that can affect the test result. But testing the effect on impurities and the hydrogen backbone is relevant because we know the environment and gas purity really does affect the end result. So that was one of the first circles. We have the stress level, mechanical wear, cyclic loading in the pipelines, very important to consider, and then the material, the susceptibility. Here to the far right, we have cracking in weld zones because welds make the steels more susceptible to hydrogen embrittlement. So these uncertainties need to be assessed through future testing. And we believe that these welds and the defect level in general is a key focus in repurposing the pipelines. And one example of these targeted tests, not just on small-scale specimens, but taking into account residual stress and actual defects, is a full-scale study we performed 10 years back with Danish Gas Technological Center. And it was a full section of the Danish gas grid taking out after 20 years of operation. And hydrogen 100% was cycled inside the pipe, simulating 80 years of lifetime, and also subjecting the pipe section to twice the maximum pressure variations to those in the Danish natural gas grid. And exactly the discussion on pressure fluctuation is a big one at the moment. No observed crack growth was present after this full-scale dynamic testing. UT, ultrasonic testing, and magnetic particle inspection was performed as NDT methods, and then metallographic cross-sectioning showed we have the weld here, and typically we would see cracking in these transition areas in the heat-affected zones. But looking at higher magnification, you can see that there is no crack initiation at all. And that's just another good sign that repurposing is actual. It's coming. And tests like these may help the green transition, but the hydrogen industry lacks standard. And we know that testing is going to be part of this journey. But Force Technology is also involved in standardization on a national level. We know that repurposing is not only about pipeline steels. The components in the system are also complex, and development of these standards take years. We might be able to use some of the present ones, and we have ASME B3112 for pipelines. But what should component manufacturers do while they wait? We're currently leading a project on documentation demands for components in hydrogen infrastructure, and the outcome is to be a national guideline, because this is what we can rely on, guidelines and test programs. These are part of the journey while we wait. And of course, we also need to contribute to the development of these standards. This is an example of full-scale component testing we performed. What's interesting about this one is that the housing is made from cast iron. And as we saw previously, it's not permitted for use in hydrogen environments. But would it work? Well, this manufacturer did not have any applicable hydrogen standards. So we designed a special test like we have done many times before. The test procedure involved a charging phase where we ensured simulating years of operation in hydrogen environments, ensuring sufficient hydrogen into the materials. Then we performed a functional test based on the lifetime parameters for this valve. So the amount of opening and closes, the pressure cycles, and of course the service pressure. And then in the end, a burst test was performed until leakage. And a comparison was made between valves exposed in nitrogen and hydrogen to see if there was a reduction factor in the burst pressure. We did not see a significant difference in the burst pressure. In fact, both burst pressures for hydrogen and nitrogen were a factor 10 of the design pressure. Hence, we did not see any embrittlement effect. As we can see in this center image, the weak link was the gaskets. And that's another area for investigation. But this is just an example of a test relevant to ensure the safe transition in hydrogen service, and something that we could not just look up in a table. So just to sum up, well, yes, hydrogen does enter the steel, but it doesn't necessarily cause damage. We have several parameters affecting hydrogen diffusion and dissociation at the surface, and these are currently being investigated. What is the effect on impurities in the gas? And evaluation of hydrogen materials compatibility is not simple, and we cannot put a limit on a stress level or hydrogen concentration unless we test specifically. And we know the focus is on repurposing pipeline sections, but it's also very important to consider the components. And of course, standards is needed. So this is where we move to Geir. You will talk about challenges and opportunities in repurposing existing hydrogen infrastructure.
Now I did an oopsie here with my sharing anyway. Thank you for that, Ditte.
Yeah, there will be questions in the end, I just want to say.
Yeah. Give me a second. No. Okay. Is something appearing? Let's see.
Yes.
Okay. And is everything looking correct? No, probably not. How do I? Okay. Let's see. Do you see my slide?
Yeah, it looks good now, Geir.
All right. So welcome to this. Sorry about the delay. I'll just get right into it. Yeah, my name is Geir. I'm working for Ramboll as a pipeline engineer. Been doing a lot of that for the last couple of years. Just to give a little fly-in here, why pipelines? Well, most of us know pipelines. They are the enabler of transport of large quantities of energy across distances in oceans and valleys and so on. We use them as short-term storage if there is a mismatch between supply and demand, or if there's periods of extremely high demand. And they are a very well-established technology for the conveyance of gases and liquids. And they resist a vast infrastructure for the natural gas, and the hydrogen infrastructure will also need pipelines. So here you see the current map of the so-called European hydrogen backbone with new and old pipelines, the green lines representing repurposed pipelines and the yellow one representing new pipelines. This is the vision for the European hydrogen infrastructure. So a lot of pipelines. Here in Ramboll, we have been actively working on various types of hydrogen pipeline projects. They are for offshore and onshore applications across different geographies and to different levels of degree, where in some cases we are studying or comparing the repurposing of an existing pipeline to building a new pipeline. And in others, we are simply designing new pipelines. And just a couple of snips from our study. So, yeah, so we've done comparison studies the potentials of specifically the North Sea pipelines, and there are various onshore pipeline projects which are in various phases concept studies to some more detailed studies. A brief overview of hydrogen pipelines. The carbon steel has been used for hydrogen pipelines for almost a century, so we don't see that as a novelty per se, although they are usually with relatively soft steel compared to the modern natural gas pipelines, and shorter distances and even lower pressures. But there is a lot of knowledge in industry experience, and the ASME hydrogen pipeline code acknowledges this, that there is vast experience, but the more laboratory data is needed. Hence, people like Ditte. We see a lot of similarities between the natural gas or methane pipelines and the hydrogen pipelines, but there are some key areas where there's difference. Main point being there's restrictions on material selection, either considered unacceptable, but or that you need to add additional safety factors. There is a susceptibility of fatigue crack growth. Well, if the crack starts and if the hydrogen is attacking it, then we see a more rapid fatigue crack growth compared to the natural gas. There is some discussion on the velocities because due to the lesser energy density of hydrogen compared to natural gas, then it seems on the surface of it that the energy transport is only going to be a third of the natural gas. But since it's such a small molecule, it can flow a lot faster. So when we compare flows for identical pressure levels between natural gas and hydrogen, we see the hydrogen partially or up to 80% compensating for or matching the energy flow of the natural gas by 70-80%. But this all in turn turns into very high velocities in the pipeline. So the question as a pipeline designer is, can I allow for 100 meters a second hydrogen transport, or am I limited to something else, or should I lean on the erosional velocities typically used today and for natural gas? Point 4 here is the pressure fluctuations. Obviously, the hydrogen pipeline is different than the way that it's a natural gas field is a more or less constant producer of of natural gas, but the renewables are not as constant. So what about the pressure fluctuations? I'll get back to that a little later. And also, if you want to use the pipelines as storage, then it obviously means you pressure it up to pack more into it and then release it what is the allowable limits here. And then, of course, the whole discussion about components, valves and compressors. I'll get a little bit into that as well, but was quite insightful what the Ditte was showing us. So since hydrogen pipelines exist, and of course there are some guidelines and standards available. The main one we consider is ASME B3112, but IGA, the European Industrial Gas Association, has compiled a sort of best practice, and the IGEM in the UK has also come up with a supplement tool to their TD1. We'll look a little bit back into these a little later. There's also guidelines on repurposing from different organizations, also included in the ASME and the IGA documents. And there are new codes coming. Most notably, in my opinion, or for my purposes, the GNV GIP called H2 pipe on specifically offshore hydrogen pipelines. So a sort of extension or addition to their well-known DNV STF 101. Let's take a little look in the recommendations in the standards on material compatibility. Just focusing on the highlighted words, then the ASME is saying that you should use X42 or 52 unless you do more qualification, and if you do not meet this qualification, you limit your hoop stress to 40% of the yield strength. There's a similar phrase in the IGEM. It's even more stringent, limiting the allowable stress in the pipeline to 120 megapascal, which translates into a utilization of somewhere between 0.25 and 0.3, depending on the yield strength in the pipeline. And then the IGA has a X52 or lower recommendation and limit to 30% of the yield strength. So it's every code is having some restrictions, but they are not identical across all of them. So just to demonstrate a little bit the effect, and here I'm following the design procedure of the ASME B3112, so-called option A, which means that you only verify the toughness of the steel and the ductability, and then there's a set of safety factors which come along with that. I'll get better into another option called option B later. So a particular aspect of this option A of ASME B3112 is this HF called the material performance factor. And I'm just going to take a little bit an example here where I have API 5L X70 steel, so yield strength of 485 megapascal, and we put it at ambient pressure. We put it on location class 1, which basically means it's out there in the field, far away from humans, and we put the temperature derating and the longitudinal joint factors to 1, so just to consider sort of normal conditions there. And then we go into our table, and so S would be the yield strength, T is the wall thickness, and D is the outer diameter, and P would be the resulting allowable pressure. So we go into a table in ASME B3112 and we look up our material performance factor, HF, and let's just say we stay below 137 bar, and we are working with X70, so here it is. We should select HF as 0.00776. And then we have another safety factor, or F, the design factor, which for natural gas pipelines would be, for location class 1, would be 0.72, but here we are limited to 0.5, so we multiply the two together, and we get the 0.338 multiplied to our allowable pressure, which is should be compared to 0.72 for natural gas. So just from the economics of designing a pipeline, this either results in a significantly reduced pressure or significantly increased wall thickness, which is expensive. And this is a little bit debated, this conservative approach, and what Ditte was showing you as in terms of material data, we're not seeing that large of an effect of hydrogen compatibility based on yield strength alone. And there have been voices, and I'll get a little bit back to that, that the argument could be made that the material performance factor is not fully utilizing the test data we have today. And ASME has even come up and said this themselves, that there is no relationship between yield strength and fatigue crack growth rate. And here's an example of another interpretation that, and this is written in 2015, so 4 years before the ASME was updated, that since the data for these different material types fall within each other's experimental scatter bands, the ASME B31 committee is drafting a new code which removes the materials performance factor for X70 and below. This is not materialized yet, and there are so different levels of anticipation of how this will evolve in the future. But the design codes being what they are, the industry is in a rush and has already, here's a couple of examples. Qualification to 100% hydrogen application is already ongoing within many industries. And I just take some random examples here. Here's RMA, which is a pipeline equipment, ball valves, vents, and so on for pipeline transport. They have cooperated with a certification agency and obtained certification for hydrogen transport. Europipe, which is a major pipeline producer, has tested their pipelines and including their epoxy flow code, and have not identified any issues. And ArcelorMittal and Corinth Pipeworks has likewise come out and said that they can offer hydrogen certified pipelines. So there's a bit of a disconnect here. I think the industry is running ahead and of course doing the proper qualification programs, but basically demonstrating that their current products are suitable. And just to come a little bit back to the test, which Ditte mentioned, then this test was run at a pressure cycle of corresponding to twice the operating pressure cycles from 40 to 70 bar, and this is a utilization of up to 0.52, which is relevant to compare to the recommendations of 40%, 30% shown before in the different codes. So promising results to say the least. A brief detour here into offshore pipelines. Like I said, I'm anticipating the rules coming from DNV in the near future. But here I just want to mention a little bit that offshore pipelines are not designed purely like the onshore pipelines, purely for pressure containment and in some cases crossings and so on. But the wall thickness is often determined by installation loads. And just taking a little example here, but if I design a 28 pipeline in X70 steel for 120 bar design pressure, the pressure containment will only require me to have 8.4 millimeter steel, but checking all the other limit states, specifically referring to the DNV offshore pipeline design, then I'm being pushed up to 12.1, and then I round up to a standard thickness of 12.7. So already I'm speculating if static flow lines, which obviously need to resist the installation loads, are if we're getting some free reduction in utilization in some cases. But of course, offshore pipelines are exposed to a lot of forces and waves and currents and so on. So which also needs to be considered, not just hydrogen compatibility. But the pressure fluctuations, again, revisiting these, the wind and sun is not producing in constant levels. And if we're going to use the pipelines as storage, like we do for the natural gas pipelines, then we need to make sure that they are compatible. And there are limits where there is no effect, but like Ditte said, then I think there's a way forward by looking into the defects and the flaws and sort of calculate if these are a source of high fatigue rack growth. And we have done this in a study, but I think the industry needs to align a little bit on the effects. And just a little bit more on pressure variation and fatigue. Then we see also that in some cases, especially these early phases of projects, then they're often thinking of imposing operational limits in terms of pressure specifically. What happens if there's no wind? Do we allow the pressure in the pipeline to decrease, or do we maintain it at a certain minimum level? And how can we use the pipeline as a storage? These early thoughts, but like the tests are showing, then maybe we are not. Maybe we should not limit ourselves too fast or too early, since the data is still coming in, and and conservatism might be excessive. And the industry, like I said before, it's moving ahead with repurposing as well as being certified for new equipment. There are guidelines in various guidelines, like I mentioned, the ASME and the IGA contain something, and there's a red thread, of course, in all these, that you do a condition assessment and you review the operational history, and you do your risk assessment, and do inspections, and you find the condition of the pipeline where the flaws and defects are, and so on, and you do some cleaning and whatnot. And this top figure here is showing a pipeline in the Netherlands, which was previously a natural gas pipeline, but has now been repurposed, connecting two industries and pumping hydrogen from one of them to the other. The approach in this article was not the same as given in the ASME code, although it is written just about the same time. Which is interesting, but well, they basically just did it, and now it's a hydrogen pipeline. So, and recently the pipeline system NGT, or Norgors Transport, and NOHAT obtained a certificate of fitness for Bureau Veritas for transporting 100% hydrogen. This, of course, certificate will have some limitations, I suppose, but the materials have been, and the pipelines themselves have been inspected, and the materials evaluated to come up with this certification. So there's quite a lot of movement, and things are actually happening, although there are skeptical voices, of course, but it's understandable. One more aspect on repurposing is the sampling requirements, which is something which makes a laboratory like Force Technology very happy, but for a pipeline engineer, he would think, but I'll get back to that. But there are quite extensive sampling requirements which for sure do not become relevant for offshore pipelines, that you cut out material samples per 1 mile or 1.6 kilometers. Otherwise, you are severely penalized in the allowable pressure. So another approach, and this is something we did together with Force Technology for a study, is to do a weakest link analysis, where we go through the inspection records. We identify what we saw as the major flaws and defects, and even doing a evaluation on some sort of standard defect, just a conservative standard defect, and then calculating for a particular number of pressure cycles at a particular level to calculate the lifetime of this pipeline. And we think this would be a sort of a more targeted approach for a specific pipeline than doing extensive sampling from which potentially induces a lot of harm for the pipeline. So that being said, just a brief sort of summary here. Pipeline steel, and this is sort of covering both sections of this webinar. Pipeline steels have been extensively tested, and there are very high similarities between the common pipeline steel grades we see in the market, which is typically something like X52 to X70, but X80 has also shown some promise on the material performance. There are a lot of conservatism in the design codes and guidelines compared to the natural gas pipeline design codes. And this is probably something very reasonable to do, but it seems that the signs of relaxation would be maybe with some conditions or with some additional testing applied, that there's coming there's coming more room to relax some of these, or at least for the pipeline designer as myself, some sort of a practical way to not design with too much steel or with too low yield strength or with for too low pressure. Already the hydrogen has a disadvantage in its lower energy density, and adding on top of that significantly more expensive pipelines would further jeopardize the business case. Not that the business case should be governing, the safety aspect should be governing, but if that one is overly conservative, then this is definitely not facilitating any sort of energy transition. What specifically Ditte was mentioning is that the defect level in the service history may be the most important parameters in the terms of repurposing pipelines, since there are at least indications that the pipeline structure itself, per its welding qualification and per its pipeline steel applicability to hydrogen, seems promising, the testing of these. Then the unknowns would be for specifically very old pipelines, the defects and the service history. But again, here also we have promising data for vintage steel. And the components, that is the big question. I mean, we of course realize that if you're going to transition into some sort of a hydrogen industry or infrastructure, you would need to buy all the compressors. You would need to make sure that the ATEX category is complied with, and that the suspected or known leakage sources are somehow addressed, either with some sort of free venting or monitoring and so on. But we'll take it one step at a time, see if we can use the pipelines. And by the way, the European hydrogen backbone is based on currently on the assumption that 60% of the pipelines will be repurposed. But the components, like you see in the container there, they are being tested, and they're not that horrible performance, I might say. The industry is moving forward, both in terms of obtaining its own certification, even only on its current product portfolio of natural gas pipelines. And also the components manufacturers are out there testing and obtaining certification. So the industry is moving forward, so no holding that back. And hopefully the design codes somehow will be an enabler of that in more and more. And yes, of course, the guidelines and test programs are currently the part of the journey. And as we see our tests and performing well, then we hopefully wait and see if the standards will also come into play and contribute even further. I think that was it for me.
Thank you very much, Geir.
Thank you.
Then I think we will start with some questions. Thank you to Ditte too. You will not be able to speak, so I will just take the question from the chat, and feel free to ask more questions. We have 5 minutes left. First question is addressed for both of you, I guess. It's about the end users, whether they are requiring 100% hydrogen. Maybe Ditte, you can elaborate on that.
Yes, of course, that is relevant, because if we use the infrastructure for blending, then we don't just get out hydrogen. So that's also why it's probably going to be a solution involving many things. So we have the local energy clusters where hydrogen is used on site, used to produce green fuels and other things. And then the infrastructure could be a transition phase where we have the blending, and then the end result would be a dedicated hydrogen infrastructure where you can take out the hydrogen, because yes, I agree, the end user would probably require the hydrogen in most cases.
Great. Then there's another question for you, Ditte. I think it's related to the valve test you mentioned. How did you simulate 80 years of operations?
Yeah, that was the full-scale pipeline test. It was based on the known pressure fluctuations in the Danish gas grid, and then extending these to twice the amplitude. And yes, that was basically why 80 years was the number. I think there was also one on PE or thermoplastic pipeline, because actually that project was a 10-year project, basically covering mainly polyethylene pipes, because that was the main focus and the main area of concern. And the results were quite good. And we also see today that these PE pipes actually perform quite well. And again, the application may be a different one, more a transition phase or local, where you don't have the same requirements, but it is definitely something also applicable for hydrogen.
Then there's a little bit more general one. I don't know who of you would like to answer. It's about if there exists any kind of overview of legal regulatory requirements over the world. What kind of approvals need to be achieved, like PED in the EU? Do you have any?
For components, that's what we're looking into. How much of the existing valve standards can we use? What modifications are needed? I'm not aware of a governing view or overview. That's what we're trying to create on especially on components for hydrogen infrastructure.
Yeah, I'll second that. I don't think you can just look it up. Specifically in the Danish context, there is an authority, the safety agency, something like that. Then they say, I mean, you follow the legislation for pressurized equipment, and if it's a hydrogen, then you can use the ASME code, something like that. And they would more like be looking for third-party verification rather than writing out the requirements themselves. That is at least my understanding of it.
Right. Then there's a question for you, Geir. What are your thoughts on the hydrogen velocity? What challenges to anticipate if the velocity is increased by approximately 3 compared to natural gas?
Partially, I don't expect problems, but on the other side, as an old oil and gas pipeline designer, I'm aware of aspects like singing pipes, which cause vibrations, and this is not very good. I am just waiting for the big news that someone did a full-scale test on a 20-kilometer pipeline until it began to do something. But what I hear, the rumors in the conferences and so on, is that the limits which are being discussed are quite high. So, and for me as a pipeline designer, I'm very optimistic that if you really are allowing something between 50 and 70 meters a second, maybe higher, then the energy transport capacity of the pipeline compared to the natural gas pipeline, this is always the benchmark, so to speak, that it would not be severely hampered.
And another concern, which are also considered, is the very fluctuating production of hydrogen, so that the pressure will also go up and down. So I guess that the answer is the same there. We cannot see it. It might be a problem, but we need to.
It might be a problem, but it might also not be a problem. If you have a new pipeline, I think it's obvious that you can design it against the actual operating conditions. But for a new pipeline, and this is maybe someone will give me a phone call and tell me, but the certification obtained for NGT and the NORCAT pipeline systems for sure has some limitations based on some evaluations. So, but like I said in the presentation, some clients are already now imposing limitations on themselves for specifically like an offshore pipeline producing from a large wind farm. And maybe this is very prudent, we'll see, but in this case, they are also considering repurposing existing pipelines. So we'll see where it ends, this discussion. And you can calculate it if you have the actual parameters and the condition of the pipeline.
I think time is up, and I will thank you, Ditte and Geir, for your presentations, and have a nice day.
Thank you. You too.